Everyone, Mr. Armitage here. In this video, we're going over, and in the next several videos, we'll be going over different hypothesis tests, and we'll be using the same situations as were in the Peardeck. Now, the first few videos we'll be doing, the first two will do the same ones that we did in class. The next two will have the last two that we never got to, and then there will be a third bonus one as well. So that means 5 videos total, going over all of the hypotheses, or all of the different hypothesis tests. Right, so let's get started with this one. Bankrate.com conducted a survey in 2013 and found that only 36% of adults, so I'm going to highlight that right now, because percent means that we will likely be using a proportion later on. 36% of adults over the age of 18 have saved any money for retirement. Later, a random sample of 341 adults over 18 showed 130 with any retirement savings. Is there evidence this savings rate has improved? Okay, so we talk about percent in here. And in a way, rate is also related to percent or proportion. So to write our hypotheses here, our null hypothesis and our alternative hypothesis, we need to identify what we're doing. So we're talking about percent of adults who have saved for retirement. So it's a percent, which means it's going to be a proportion. So P. And our null hypothesis is always that P is equal to some value. Now, in this particular case, it's the value that was found previously. Okay, we're taking that as the population, the actual true percentage of adults who have saved money for retirement. And then we did this survey, and what we are hoping to show is that the proportion of adults, the percent of adults who have saved has increased. So it's greater than 36%. And now with this, we want to actually figure it out. Okay, so since we're doing a proportion, okay, we know it's going to be a z-test. And we see here a random sample of 341 adults. There's only one group. One sample, one group, therefore a one proportion z-test. Okay, so now let's get down all of our information. Okay, our sample size, N, was 341. The number of successes, okay, so the number of adults who had saved was 130. And now we can combine those into our estimate, p hat. So that's x divided by n. So 130 divided by 341, which we'll go ahead and use a decimal for that. 130, 341, 0.381. Okay. So in this survey, this sample, we got 38.1% of adults who had saved for retirement. Now 38.1 is above 36, but is that more likely because of sampling error, just by chance? Or is it so unlikely to happen by chance that it actually has improved? And that's what we're doing here. So once we have our p hat value, we can finally calculate our test statistic, which is a z-score. And so any sort of z-score or test statistic for right now for us, it's always what we observed minus what we expected divided by the standard error. Now we haven't calculated the standard error yet, so we need to do that. Okay. Standard error of p hat, in this case, is going to be p times q divided by n, and then the square root of that. Okay. Now, I'm also going to write it like this, just so we can sort of see something here, in that our standard error is always the standard deviation of our sampling of our distribution. So in this case, for just one, or for this distribution, it would have a standard deviation of the square root of p times q, q being 1 minus p. So just off a little aside here. 1 minus p equals q. Exactly like the binomial model and all that. Okay, but it's always the standard deviation divided by the square root of the sample size, which is what we have here. Just because there's a square root and also the standard deviation like this, it's easy to kind of mush it all together. Okay, but our p is 0.36, which means our q, okay, 1 minus p, so 1 minus 0.36 be 0.63 divided by 341, and then the square root. Okay. So now that we can calculate that, oh wait, not 0.63, it's 0.64. Right. Okay. Multiply, divide, and square root. 0.02599. Okay. So now let's just substitute everything in to our z-score up here. Okay, so our standard error, 0.02599, p hat, 0.381, and p, 0.36. Now this is the point where I would say, if you're putting this into a calculator, be careful. Put parentheses around the subtraction, around the numbers in the numerator, because otherwise you're in for a hefty surprise as to why it does not come out correctly. Okay, this gives us a z-score of 0.808. And so we could have a conclusion here. Okay. Two different conclusions. One, this is a z-score. Okay, so we can go by the rule of two in that, okay, our z-score means that it's not at least 2. It's not greater than 2 or less than -2. Therefore, we fail to reject the null hypothesis. Okay, conclusion. Okay. We could have this conclusion here. Fail to reject. Okay. Now, all of these tests, okay, because nothing has been specifically said, we will take them as at the 95% confidence level. Obviously, if we were doing this like on our own or in a project, we could set our own confidence level. But right now, we're just going to do 95% confidence for everything. So we have this. Now, the other way we can do it is to calculate the p-value. And so you could go into the table, the z table, and look it up, or you could just bring this up. Okay, this is all fine here. Okay, we're just going to deal with this. Normal distribution, mean of 0, standard deviation of 1. Cool. And we just want one x value to calculate the probability. So we had 0.808, calculate, and here we go. It even corrects it to saying z instead. All right, and now we pick the one here that matches our alternative hypothesis. Okay. So our alternative hypothesis was that we wanted to show that the proportion was greater than 0.36. Okay. So we want to show, or our p-value will be the probability of getting a z-score at least 0.808 or more, which is 0.2095. So, sorry, p-value. .2095, which for the 95% confidence level that we were doing for, that would mean that this is greater than 0.05. So we fail to reject. Okay, both ways, totally fine. So that is the first one.